Okay, if you didn't get your stuff, it's because you weren't here while I was passing it out. It's here. And don't forget, Wednesday, we have an exam. Exam's written. It will be 50 questions like before, multiple choice. I'll fill in this time. And that's Wednesday. We've had some game reschedulings, so baseball won't be here today. We also have some people who are COVID positive. They won't be here today. So I'm going to try to Zoom. Zooming is a colossal pain in the gluteus maximus, minimus, or medius because it slows that computer down to about the level of molasses pouring. But I'll Zoom anyway. We're supposed to start on treating angina pectoris. Angina pectoris is caused by atherosclerosis. So it behooves us to look at cholesterol, like cholesterol trafficking, cholesterol regulation, since that's the cause of atherosclerosis, which causes angina. We'll look at that first, then we'll circle back to angina, and then that will lead kind of naturally into a discussion of anticoagulants. And then from anticoagulants, that'll lead nicely into NSAIDs and analgesics and opiates and so on and so forth. So that's the map essentially that we're hoping to follow. So today is cholesterol metabolism. Let me warn you, this is not simple. There's nothing about this that's simple. I'm going to try to take the cookies and put them on a nice low shelf. There'll be times when you look at it, you'll go, what? But that's okay, because Elena, you're Sarah's got your stuff. Okay. So this again, this is not simple, but it's important because cholesterol regulation is a major part of atherosclerosis. Did you guys enjoy yesterday? Yesterday to me was quintessential Michigan spring. It was just you stand out, you just stand outside in the sun and go, oh, not too hot, not too cold, not too breezy. The trail was filled with people. There were people bike riding, walking, running, walking their dogs, as it should be. It was glorious, wasn't it? And Hope sat there saying, I was doing homework all day. Hope you were outside doing homework, because it was truly glorious. So hopefully we'll have a few more days like that. And well, actually a lot more days than that. Let's just hope for that. Okay. Did you guys see the revision of the CDC guidelines? No more 6 feet, 3 feet. So 6 feet, people said 6 feet were pulled out of a hat. That's not right. 6 feet came from the influenza pandemic. Because influenza, you get mostly from surfaces and you get from aerosol. COVID-19 caused by SARS-CoV-2, you don't get from surfaces. I don't know why people are still spending all this money cleaning surfaces. There's not a single case I've heard of where someone's caught COVID-19 from the surface. It's passed by droplets, less by aerosol, mostly by aerosol indoors. But droplets and big droplets fall after about 2 feet. So that's why the CDC guidelines revised to 3 feet. What this means is that masks are far more effective than anyone ever thought. Also, being outdoors. When you're outdoors, your chances of catching COVID-19 go down 20-fold. That's 20, 20-fold. The mask gives you 80% protection. Being outdoors, 20-fold. So if you're outdoors running, do you need to wear a mask? Survey says, no. Take the darn mask off. You don't need to wear it while you're running. In Australia, you can live with your wife in a house and not wear a mask. But when you get in a car, the two of you have to wear a mask. I'm sorry. That falls under the category of moronic. That's a dumb regulation. And I would not wear a mask, and the cops get a ticket. I said, ticket me. Go ahead. The law is stupid. It makes no scientific sense. Plus, I've got the windows open. So If I lived in Australia, you're darn right. I'd drive these windows open. Okay, enough about that. Let's go ahead and dive into it. So cholesterol is a molecule that's received a lot of bad press, and I suppose rightly so, because there's a lot of it in our diets, unfortunately. But cholesterol also is quite important when it comes to your body. Every single steroid hormone in your body is made from cholesterol. So aldosterone, cortisol, testosterone, estrogen, progesterone, DEAE, all those are made from cholesterol. Cholesterol also is a hugely important component of cell membranes. Cholesterol regulates fluidity and rigidity of cell membranes. There are some membranes in your body that need to be very rigid. There are others that need to be more fluid. That rigidity and fluidity is regulated by, at least in animal cells, by cholesterol. So we need cholesterol. Cholesterol also is hugely important for signaling. The sonic hedgehog pathway, which plays a vital role in development, in neurogenesis, in the control of cell proliferation, and in wound healing, all depends upon cholesterol. So cholesterol is important for signaling, it's important for structure, and for the synthesis of hormones. Hugely important molecule when it comes to the life of humans. Now, we get cholesterol from two sources. We make our own cholesterol. Every cell in your body can make its own cholesterol. We also get cholesterol from our diet. Animal-based products contain cholesterol. If it grows in the ground, it doesn't have any cholesterol in its membranes. Plants use cholesterol as an intermediate, but they use it as an intermediate to make other things. So if you eat something that grows on the ground, there's no cholesterol in it. You eat stuff that comes from animal products that has cholesterol in it. Now, in this picture, which doesn't come out very well here, but comes out much better on my slides here, cholesterol is made from acetate. Acetate. So acetyl coenzyme A, and to give you an idea of where acetyl coenzyme A comes from, let's do a very quick primer on metabolism. Use my little makeshift blackboard here. All right, so glucose, or really any sugar you consume. Those sugars essentially either get converted to glucose or get metabolized like glucose. So glucose is broken down by this process called glycolysis. Glycolysis is universal. You see it in bacteria, you see it in ferns, you see it in green plants, fish, frogs, farm animals, people named Fred, they all use glycolysis. It's universal. Glucose, which is 6 carbons, gets converted to 2 3-carbon compounds called pyruvate. Pyruvate then goes, this happens in the cytosol. Happens in the cytosol then, at least in our bodies. Pyruvate is then going to go into the mitochondrion. In the mitochondrion, it's converted into a 2-carbon compound. So it gives up a carbon dioxide. And then this 2-carbon compound is carried by coenzyme A. Coenzyme A, so you get acetyl coenzyme A. That happens in the mitochondria. And so you're going to give up a carbon dioxide, and you're going to add a coenzyme A. Right there. Now, this goes to the Krebs cycle. And the Krebs cycle also occurs inside mitochondria. From that, you make lots of high energy electrons. Those high energy electrons are fed into electron transport chains that are embedded in the intermitochondrial membrane. Those high energy electrons then are given to molecular oxygen to produce water. And from this, you make a proton gradient. And from that, you make lots of ATP. And that's kind of the house that Jack built when it comes to metabolism. And if you eat fat instead of glucose, fat gets converted to fatty acids. Those fatty acids are broken down in the mitochondrion to acetyl coenzyme A, which goes to the Krebs cycle, which makes high energy electrons, which then goes down the electron transport chain, gets given to molecular oxygen, gets converted to water, creates a proton gradient, makes ATP, blah, 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 blah. And the punchline is you still make ATP. So essentially, acetyl coenzyme A is kind of the metabolic roads if the metabolic roads all lead to the Rome of acetyl coenzyme A. Now, acetyl coenzyme A can also be used for biosynthesis. And one of the things you make with acetyl coenzyme A, can be used also to make fatty acids. Those fatty acids are used to make phospholipids for membranes. They can also be used to make triglycerides. Triglycerides are for storage only. They don't play a structural role. They're for storage. I hedged a little there. They play a role in protection. So if you put them around organs, they protect organs, and they're also an important insulator. They tend to keep heat in. Ooh, Josh, don't do that. Ooh. Crack. Josh is playing chiropractor on his own head. Get Allison to do it. She's going to be a chiropractor. The other thing you can do with these, and there's other things, but for our purposes, you can then use this to make cholesterol. And so if we then go back to our slides, I feel like this thing is powered by high performance squirrels sometimes. Come on, squirrels. There. So this carbon, this carbon, this carbon, this carbon, this, all the carbons in cholesterol come from acetyl coenzyme A. So if you take this acetate, this carbon here, and you paint it red, that carbon's red, that one's red, 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 red. Every other carbon is red. So all carbons found in cholesterol come from acetyl coenzyme A. I think I need to call Cynthia. I'm not sure this should be happening. Okay, there. All right. All right, so cholesterol gets made from the same metabolic intermediate that's made in glucose, fat, and protein degradation. That's the upshot. So, can you make more cholesterol if you eat a lot of sugar? Yes, because sugar makes acetyl coenzyme A. You make cholesterol from acetyl coenzyme A. Can you make more cholesterol if you eat a lot of fat? Yes, because fat is broken down to acetyl coenzyme A. What do you make cholesterol from? Acetyl coenzyme A. Can you make a lot of cholesterol from eating a lot of protein? Yes, because proteins are broken down to amino acids. Most amino acids are broken down to acetyl coenzyme A. What do you make cholesterol from? Acetyl coenzyme A. So the litany should let you know that you make cholesterol from components that come from your diet. And here's how you make it. And I'm going to give you the Reader's Digest version on how you make it. So you take acetyl coenzyme A and you link them together. And you make two, you take these two, you link them together, you get something called acetoacetyl coenzyme A. Acetoacetyl coenzyme A. And then you take a third acetyl coenzyme A and put that with acetoacetyl coenzyme A, and then you make this molecule here, HMG-CoA, which stands for beta hydroxy beta methyl glutaryl coenzyme A. We're just going to abbreviate that HMG coenzyme A. Is that okay? Yeah, I figured that was okay. That's okay. HMG coenzyme A. Now, HMG coenzyme A is reduced. It's reduced. Corinne, when you reduce something, what do you do to it? When you reduce a molecule, what do you do to it? No, that's oxidation. Yeah, there you go. Add electrons. Add electrons. So we're going to add reducing equivalents. We're going to add electrons and hydrogen ions. And HMG-CoA is going to be converted into this molecule here, mevalonate. Mevalonate. Once you make mevalonate, you're committed to making cholesterol. Disco light. Mevalonate. And the enzyme that makes mevalonate from HMG-CoA is HMG-CoA reductase. Does not come out very well. That's not erasable. That's not erasable. Where's the? Oh, somebody's been feeding on dry markers. How nice. This is the rate limiting step in the synthesis. Therefore, it is the most highly regulated step in the cell. If you want to stop cholesterol synthesis, you stop it right there. And the most important drugs we're going to look at in regulating serum cholesterol levels inhibits this step. It's vital you understand this step here, that this is the bottleneck, if you will, in cholesterol synthesis. You make mevalonate. Write that name down and make sure that you can rehearse this when you get up in the morning. mevalonate, mevalonate, mevalonate. Yeah. And so on and so forth. Okay, what do you do with mevalonate then? Mevalonate is then rearranged. You put some double bonds in it, and you make these isopentenyl molecule. Then you link those isopentenyls together. You make polymers of these isopentenyls until you get this big molecule that's 30 carbons long, and that is called farnesyl pyrophosphate. And then this enzyme called squalene synthase takes that and makes rings out of it. It takes all these and clicks them together and makes rings, and it converts squalene into lanosterol. Lanosterol. By the way, squalene, you classic scholars out there, anyone know how you say shark in Latin? Anyone? Squalus is shark. So guess where squalene was found? In sharks. And if you dissect a shark in high school, remember how much it stank? Remember how greasy it was? That's squalene. Sharks are loaded with squalene. That's why they're so greasy. That's where the molecule was first discovered and isolated from. That's why it was called squalene, because it was from sharks. So lanosterol is then taken through a series of about 15 steps and is converted to cholesterol. And that's essentially how you make cholesterol. But this pathway is also used to make isoprene repeats. And these isoprene repeats are used to make several other molecules. And so they're used to make things like carriers in the body. So your body uses glycol to carry carbohydrate trees that's going to stick on proteins. And then this is coenzyme Q10. Heard of that? That's what ubiquinone is. Runners back in the 90s used to take coenzyme Q10 as a supplement before races to help them perform better. And they don't much anymore. But coenzyme Q10 is used in the electron transport chain and is used to help your cells make energy. And you make that from precursors that come from the cholesterol pathway. That's why inhibiting this pathway can have some side effects like muscle aches and muscle breakdown and things like that. Okay, which step is the bottleneck in all this? I don't speak mumble. Thank you. The synthesis of mevalonate. The synthesis of mevalonate by the reduction of HMG-CoA by HMG-CoA reductase. Beta-hydroxy beta-methylglutarate coenzyme A, exhale. Or gesundheit, maybe you'd say. Now, in cells that can make their own vitamins, your fat-soluble vitamins get made from this pathway as well. We can't make them. We need these in our diet. But let me also say, vitamin D is made from this pathway because the penultimate step in cholesterol synthesis, you make 7-dehydro. You make 7-dehydrocholesterol. If that gets irradiated in your skin by UVB light, that then is converted into vitamin D3. Vitamin D3 then needs to be hydroxylated by an enzyme in the liver. The alpha-1 hydroxylase, then it needs to get hydroxylated in the kidney. The alpha-1 25 hydroxylase to make cholecalciferol or vitamin D. Now, in fungi, lanosterol goes through the same first 4 steps, and then it takes a turn for the different, and instead of making cholesterol, it makes ergosterol. Why is this important? Because this pathway from lanosterol to ergosterol is the target of most of your major antifungals. So drugs that are used to treat many of your systemic fungal infections are the azole drugs. They end in azole or con-azole, keto-con-azole, flu-con-azole, itra-con-azole, posa-con-azole, isuva-con-azole, your mother-in-law con-azole. They attack essentially the synthesis of ergosterol from lanosterol. And because the enzyme is sufficiently different in fungi from mammals, these drugs work rather well without causing too many side effects, at least. In humans, some cause more side effects than others. And these are some of the azoles. And these azoles, miconazole is a topical drug. So is clotrimazole. Trade name. Gynolotrimine. Have you heard of gynolotrimine? That's clotrimazole. And then miconazole is used in athlete's fungus sprays. Mycotin, I think, is the name of one. And some other product on this. You can go down to Weatherwax and look and see products. Those are used for what we call ringworm infections. They're not caused by worms. They're caused by fungal infections. I see Elena nodding her head. She's seen those probably. And they can itch. They're nasty sometimes. They're not very pleasant. Okay, what happens to cholesterol once you make it? Cholesterol is not very soluble, but cells need it. Now, the big maker of cholesterol in your body is the liver. Other cells can make cholesterol. They may not make as much cholesterol as they need. So the liver will make lots of cholesterol and then deliver it to the body. It can't just kick it into the bloodstream. It'll precipitate out. So what do you do with something that is hard to transport? You put it in a taxi. You put it in a taxi. And to illustrate this, let's use a very silly example. Let's say Kaylee back there. Let's say Kaylee is an extremely dangerous person. Let's say if she comes into a room, she's kind of like, if you've ever seen the movie Serenity, she's kind of like River Tam. She just goes off on people and starts beating people up. Let's say Kaylee is incredibly dangerous. She walks in and she beats people up. So she sends Chapman to the hospital, and then she scares Katie half to death, and then Zach now has to walk on crutches all because of Katie. She's dangerous. We can't just let her be on cameras. So she needs to get to the field house. Can we just let her walk the field house? No, she'll leave a trail of carnage to the field house. So what do we do with Kaylee? We put her in a taxi. That way she just damages the upholstery. She won't hurt anybody. So you do the same thing with cholesterol. You put it in a taxi, just like our dangerous Kaylee back there. So what's a taxi you put it in? You put it in something called a lipoprotein particle. Which sometimes gets called a lipoprotein. Lipoprotein particle or a lipoprotein. Now, to put the cholesterol in to the lipoprotein particle, you just don't wind up and say, batter up, here it goes, boom, No, you have to load it into the particle. And to load it into the particle, you need to convert it into something called a cholesterol ester. A cholesterol ester. So the enzyme that converts cholesterol into a cholesterol ester is called acyl coenzyme A cholesterol acyl transferase, which is mercifully abbreviated ACAT. ACAT. So my stupid way of trying to remember this essentially is to think of you're trying to get the cat into the cat carrier. So to get the cat into the cat carrier, you need to pull its tail. If you pull its tail, it dashes into the cat carrier, and the enzyme that does that is a cat. Big cat. And here's the tail on the cholesterol. This fatty acid right here. That's the tail. You pull the tail on a cat, and it runs into the. Okay, I know it's stupid. Lydia's sitting over there going, I don't believe this. But you'll remember it, right? ACAT makes a cholesterol ester. The cholesterol ester can now be loaded into the lipoprotein particle. It gets loaded into the lipoprotein particle because cholesterol has that hydroxyl group over there. What do we know about hydroxyl groups from your chemistry days? Polar. It's polar. The inside of a lipoprotein particle is very non-polar. So we need to do something about that so we convert it to an ester. Which is more polar, hydroxyl groups or esters? Hydroxyl groups by quite a bit. So you turn this into an ester, and now it's much less polar. It gets loaded into the lipoprotein particle. All right, into they go to the lipoprotein particle. That'll help assemble the lipoprotein particle, and now it's ready to be shipped. So growing tissues require cholesterol. Healing tissues require cholesterol. Tissues that are being remodeled require cholesterol. So let's say Jesse here gets, somebody slides in the home, spikes up, and they catch Jesse here right in the shin, right underneath her shin guard. On the shin. Kind of kicked in the shin one a few times. I'm sure it really hurt. Okay, so Jesse gets knocked down. She comes up limping, but let's say the story ends properly. She tagged her out. She's out. But Jesse's now getting. When she gets up a little bit, and then the next day she's got this nice big shiner on her ankle, and she walks around and she's favoring that leg a little bit. She's got a bruise. She's got some muscle damage and maybe even a bone bruise, perhaps, because those spikes. Because although on softball you don't wear the deep spikes, they don't baseball, you wear the shallow spike, right? Yeah, but they still hurt, I'm sure. Okay, so now in a baseball game, if someone slid spikes up, you'd probably empty the dugout. But women, you know, are much more civilized. You're going to just point and say, warning, or they should get a warning. I don't know, maybe we'll empty the dugout. Maybe, never know. Because you guys protect your catcher, right? Darn straight. Okay, so let's say but she's gimping a little bit. That tissue needs to heal. So what's that tissue going to need to heal? It's going to need cholesterol. She has to remake blood vessels. She has to replace damaged skin. The muscles that have been damaged need to be remade and revascularized with bone, which got bruised through the surface. Now the dead cells need to be discarded, phagocytized, their materials metabolized, and then replaced. All that takes cell division, all that takes, new cells, all that takes are for cholesterol. That area, therefore, is now going to become a cholesterol sink during that time. It'll receive cholesterol in the form of these lipoprotein particles. And this solves the problem of cholesterol insolubility, because now cholesterol is ensconced within a particle that is much more soluble than the actual cholesterol itself. So what do these particles look like? They look like this. They have a layer of phospholipids on the outside. And on the inside, they have cholesterol esters and triglycerides or fats. So here's a picture essentially of what these look like. So on the outside, you see a single layer of membrane phospholipids embedded in that phospholipid layer is free cholesterol. So do lipoprotein particles carry free cholesterol? The answer is yes. Do they carry much free cholesterol? No. On the inside then, you see the things that look like E's? Those are triglycerides, which we also know as fats. Fats aren't very soluble either. These particles are used also to carry fats. And then those things that look like sea cucumbers, they kind of look like sausages that are having an aneurysm. Those are meant to be cholesterol esters. Cholesterol esters. The cholesterol esters are in the core of the lipoprotein particle. The free cholesterol is in the phospholipid membrane on the outside. All lipoprotein particles, be they VLDL, LDL, HDL, whatever, have this structure. All right, let me stop right here, see if everything's gone down with a bit of coffee. Yeah, Elsa?
If HDL and LDL have the same structure, what makes one bad?
We're going to get to that. By the way, I don't like the term bad cholesterol, good cholesterol. When you say bad cholesterol, it sounds like you're putting cholesterol on the table and you're going, bad cholesterol, you've been so bad. The cholesterol sitting there going, what? What did I do? I'm just being mean. Oh, good cholesterol, nice kitty, good cholesterol. Cholesterol is cholesterol. It's essentially the particle. It's the particle and the function that the particle has that determines whether it's good for you or bad for you. In fact, LDL is actually good for you. It's when you get too much of it that it becomes bad. So I'm not a fan of that, but that's the term they use. Now, see that green glob on the top there? You have proteins that are embedded in the surface of the lipoprotein particle. These proteins are called apolipoproteins. Apolipoproteins. These are going to determine what kind of particle you have. They're going to act as the security card, essentially, for the particle. That's how your body is going to determine what kind of particle it is and what sort of functions it will have. And there is on your notes on page 57 and 58, there's a table of some of the different human apolipoproteins and what they do. These apolipoproteins are extremely interesting structurally because one side allows them to interact with the hydrophobic core of the lipoprotein particle. But the outer portion allows it to interact with the water-soluble bit at the surface. So these structurally are very interesting proteins. There's been a good deal of structural work done. All right, so these plasma lipoproteins, they're large macromolecular complexes. They have an outer phospholipid layer. Embedded in that phospholipid layer are these apolipoproteins. They have varying combinations of cholesterol esters, phospholipids, triglycerides, free cholesterol, and so on and so forth. And here are some pictures of some of these different plasma lipoproteins. And on page 59, you have a table of these different types of particles. So the biggest and the least dense particle is called a chylomicron. Chylomicron. And that particle is made by the cells of the small intestine. The cells of the small intestine. And the next biggest particle is the VLDL, very low density lipoprotein particle. That's made by the liver. And in its sojourn through the body, it gets converted into an LDL, low density lipoprotein particle, the so-called bad cholesterol particle. And then a different particle, that's more of a regulatory particle, is the high density lipoprotein or HDL particle. And if you look at the density of these particles, you will see that the density gets higher as you go from chylomicron to VLDL to LDL to HDL and so on and so forth. Now, if you go to the table on the lower part of page 59, you will note that each of these particles has a different set of apolipoproteins in their surfaces. These different sets of apolipoproteins are quite important because they're going to determine the function that these proteins have. So let's take a look at each particular particle and how it does its business. And a pictorial representation of this is shown on page 60. So if you have page 60 nearby, go ahead and have a look at page 60. And hopefully if you follow this discussion on page 60, and then you can scribble on this as much as you want to try and clarify this as much as you want. So let's say Josh over here goes into town with some buddies of his, and let's say he goes to Outback, and he has a New York. Let's say he has a New York cut steak, medium rare, medium rare. Okay. This man knows steaks. Okay, so his New York cut steak is a medium rare. That steak has in it cholesterol, and it also has some fat. Fats will be degraded by pancreatic lipase with help from bile salts that are made by the liver and released by the gallbladder into the small intestine. The fats will be reabsorbed by the cells of the small intestine, the enterocytes of the small intestine. So will the cholesterol. Cholesterol will be converted into cholesterol esters. The fats that were degraded into glycerol and free fatty acids, after they come into the enterocytes, will be remade into fats. They'll be remade into fats. The fat and the cholesterol esters will be loaded into a lipoprotein particle called a chylomicron. The chylomicron is then released on the basal side of the enterocyte. However, it's too big to enter the bloodstream. So what does it do? It enters the lymph instead. It goes into the lymphatics. There is in your intestinal each of your intestinal villi, there is there's a single lymph vessel that goes into each intestinal villus. It's called a lacteal. A lacteal. And these cells will secrete their chylomicrons. They'll go into the lymph. And they will begin their life essentially in the lymph. Now, will it stay in the lymph? No, because lymph eventually joins up with the blood. Where does it do that? Pull back to 263. The thoracic duct. The thoracic duct. The lymph dumps into the subclavians in the thoracic duct, and then it becomes part of the blood. So it does become part of the circulation eventually, but it starts out in the lymph, and that actually gives it an advantage. While it sojourns through the blood and the lymph, it's going to interact with other particles. Now, what apolipoprotein does a chylomicron have? You can turn back to your table and you can see it has apo B is in Bradovich, 48. Apo B 48. Why is it called apo B 48? Because there's 48 kilodaltons in size. Apo B 48 is particular to chylomicrons. That's the badge of a chylomicron, is apo B 48. And while it is in circulation, it will interact with other particles and it will pick up some proteins called of the apo-C, the apo-C group. In particular, apo-C2, apo-C2. Now, if you go to your table and ask, what does apo-C2 do? apo-C2 activates lipoprotein lipase. Lipoprotein lipase. So when it picks up apo-C2, it's now going to be able to interact with lipoprotein lipase. Well, so what? Well, lipoprotein lipase is found on the endothelial cells of capillaries that feed various tissues. Now, glucose is used mainly by the brain. Other tissues tend to not use glucose in order to spare glucose for the brain. So what do they use instead? They use fatty acids. Skeletal muscle uses fatty acids. Cardiac muscle will predominantly use fatty acids. Let me call that resting skeletal muscle uses fatty acids. When you get out on the soccer field and you leg it from one end of the pitch to the other. And your muscles go anaerobic, you're not using fatty acids anymore, you're using glucose. But resting muscle use fatty acids. Kidney will predominantly use fatty acids, so on and so forth. So one of the places from which they get those fatty acids are chylomicrons. Chylomicrons will come up to the endothelial cell. They'll interact using ApoC2, and ApoC2 activates lipoprotein lipase. Lipoprotein lipase degrades the fat inside the chylomicron, and it causes the chylomicron to leak fatty acids. When it's activated, it degrades the fats inside the chylomicron and causes the chylomicron to leak fatty acids. By leaking fatty acids, essentially, the chylomicron is leaking food to the tissue. It's leaking food to the tissue. So right now, as Remington sits there and writes and thinks that bagel and butter that he had for breakfast, the fats in the butter right now are feeding his skeletal muscles, thanks to the chylomicrons that were made by his small intestine. And that's happening right now. That's feeding his muscles as he sits there and rants and writes. And that's also happening to Jessica, because she had milk and cereal for breakfast. I'm just guessing. Maybe you had pancakes. I don't know. Now, what have you? It's happening right now. So here is the structure of lipoprotein lipase. I show this to you just to show you this protein's been worked on. People understand the structure of the protein. People know how it works. People know how ApoC2 interacts with it and activates it. You can see the active site there. It kind of has a little kind of clamping thing going on there. That's how it's going to clip those fatty acids from the fat. So ApoC2 activates LPL. This means that as the chylomicron circulates through the lymph and the blood, it gets depleted of fatty acids. It gets depleted of fatty acids. That's a good thing, because it's feeding your tissues. Since JP is a climber, a lot of the snacks I've seen advertised in these magazines for climbers tend to be foods that are high in fats. And I think this is my thinking and the logic behind that. As you're climbing, you're not scrambling, you're climbing, you're trying to keep your heart rate within that fat burning mode, so that as you're climbing, your muscles are using fat mainly. And as they're using fat, essentially, that's why you're doing things like nuts and other types of things that are high in unsaturated fats. You're feeding your heart, your skeletal muscles, and things like that. And that's why you climb at a moderate pace. You're not climbing at a sort of pace. Well, you might do that in your training. But if you're climbing, you're trying to keep your heart rate within that range, and that's why you're eating fatty-rich foods. Does that make sense? Yeah. Because most people I know who climb, they're not sitting there. They're very deliberate about the pace and what have you. Now, that fat depleted chylomicron becomes known as a chylomicron remnant. A chylomicron remnant. And as it interacts with other particles in the blood, it will acquire an apolipoprotein called ApoE. ApoE. E as in excellent. ApoE will allow the remnant to be bound by the liver and removed from circulation. Once it acquires ApoE, its removal by the liver is very fast because there are multiple receptors that recognize ApoE. Now, the fats and cholesterol in that remnant will be used by the liver to construct a particle called a VLDL, a very low density lipoprotein particle. The VLDL is a major transportational plasma lipoprotein of your body. It's used to transport fat and cholesterol to extrahepatic tissues. Incidentally, one thing I haven't talked much about because it's not really been studied very much. One of the major users of cholesterol is actually the brain, and how these particles interact with the brain. It's still a bit of a black box. That's still not well understood. But it's clear that the brain uses a lot of cholesterol, and it's clear that hypercholesterolemia plays a role in brain pathology. But how the brain takes up cholesterol and uses cholesterol, it's clear it's different than other tissues, but that's still a field that is kind of demanding some good PhD dissertations to kind of unlock some of the things going on in the brain. Okay, so we'll stop with the VLDL and we'll pick this up on Friday. Don't forget on Wednesday, we have a exam. If you need to take the exam at a different time or in a different place, I contacted, asked, they have the exam. Well, they will have the exam by this afternoon and you can take it there. Just make sure you make an appointment with Amber. Thank you.
I have a quick question. Was like quiz number 4.
Yeah.
So for the number 3, it was the spironolactone
Uh-huh.
and what it antagonizes.
Yeah.
And I did see in the notes that it was aldosterone primarily, but it also does, didn't it? You